Okay, hello and welcome back. Today we're going to talk about thermochemistry. Thermochemistry, in my opinion, can be simple but also confusing. I think it can be simple because if you memorize a few equations and you can rearrange those equations, you can get the answers you need. But it can be confusing because the terminology is difficult to grasp. It's sort of abstract. And that is why in honors chemistry or introductory chemistry in high school, maybe even AP chemistry, you sort of just concentrate on some basics. And I'm sure there's entire classes where they're just about thermochemistry in college and they go into detail and depth and they include physics and a lot of math, but we don't need to do that. So let's go ahead and look at just a couple of terms really fast. What sort of units do we use with thermochemistry? Well, the most common are the joule. We have a small calorie. I say small calorie because it has a small c, and a large calorie. These are units of energy, basically. So just like anything, they are units that somebody came up with, and we have assigned numbers to them now. So basically, one small calorie, here we have a calorie, equals 4.184 joules. These are going to be common units you see in thermochemistry a lot, so you should be able to convert these. Now, if we take 1,000 of these small calories, they are equal to one large calorie. This large calorie is the type of calorie that you would see on food packaging. Now, what does this really mean? How much energy is this really? Basically, one calorie, one of these small calories, is enough energy to heat 1 gram of water 1 degree Celsius. That's the definition of a calorie. So I guess one food calorie is 1,000 times that amount of energy. So next time someone asks you what a calorie really means, you can tell them. Celsius is obviously a unit for temperature. You could always convert to Kelvin by adding 273. I sort of round off a little bit. Anytime you have Celsius, you can add 273 to get Kelvin. Specific heat. This is a term you see a lot. Specific heat means the amount of heat needed to raise 1 gram of a substance 1 degree Celsius. To take 1 gram of a substance and raise it 1 degree Celsius. Now, where do you find specific heat? Basically, these are going to be given to you in the textbook or on a test, and they have tables in chemistry that you can refer to. So it's not something you're expected to memorize. Let's go ahead and look at this really fast. For instance, this table gives you the specific heat of water. Now, one thing to keep in mind is the specific heat of a substance depends on the phase of the substance. Notice this is solid. So the specific heat for ice is 2.06 joules per gram Celsius. But if this is water, so now it changes to liquid, it's actually a lot more energy per gram to raise that gram up 1 Celsius, and then it's slightly different for gas. Basically, these energies vary because of the intermolecular bonds between those different phases. They're going to be weaker or stronger, therefore you need more or less heat to break those bonds. And as we notice, they vary for other substances. And normally the units are joules per gram Celsius, but yet again, you need to pay attention to these units because they could be different. Maybe they are going to give it to you in calories or something. It's always really important in chemistry to pay attention to your units and make sure that you can convert them. I can't tell you how many times I've missed something because I haven't done that. Okay, so you notice that's what specific heat is. It's different for every substance, and it's also different for the phase the substance is in. Okay, there's this really weird word, and I think this is what confuses people a lot, called enthalpy. Basically, in introductory chemistry, people just sort of equate it to heat. They just say, well, it's heat. But it's important to know that enthalpy isn't necessarily heat. Enthalpy is the internal energy of a substance, which is affected by heat. So the actual definition is, if I say the heat given off or absorbed when a reaction is run at constant volume and temperature is equal to the change in the internal energy, or enthalpy. So if I have some substance and I'm putting heat into it, I can measure the temperature of this before I put the heat in. And then after I put the heat in, I measure the temperature. And then I can make a calculation and say the internal energy of this substance is now different. The enthalpy is different. So enthalpy is related to heat, but enthalpy also relies on constant pressure and volume, which we're not really going to worry about here in this class because all of these calculations take place at sea level, so it's assumed that the pressure is all 1 atmosphere. And also, this is why in chemistry sometimes they do these little experiments with these calorimeters. This is a coffee cup. It's pretty basic. You just have a couple of styrofoam coffee cups and you have a lid. And inside the coffee cup, you might have this little reaction going on. Notice this is a coffee cup inside of a coffee cup to insulate it. And you have a thermometer stuck through here, and we can stir it. So the idea is that you take the temperature before the reaction starts. So you have a starting temperature. Then so you have your starting temperature, initial. The reaction goes for a while, then you have a final temperature. And we can say the difference in this temperature is the difference in enthalpy. This heat that we put into the system has changed the internal energy of this system. So the reaction in the coffee cup is called a system. And around the coffee cup, all of this out here is called the surroundings. Now, why is this important? Because this has a constant volume inside. Think about it. Gas can't escape from here. It's trapped in here. So the volume is always the same. The pressure is the same. Therefore, we can say the heat that I put into this coffee cup or take out of the coffee cup is equal to internal energy, or enthalpy. And from what I understand, you can't really calculate the enthalpy of a system without putting heat into it or out of it. We can only really change the heat in the system and make a calculation. I can't just say, oh, the enthalpy of this system is whatever. So enthalpy is directly related to the reaction and to the heat. And normally there's a little formula for it, which we will go into later, and it's nothing to be scared of. Okay, that's important to know because if I go up here, this says the heat of fusion, the heat of vaporization. Well, these actually are called enthalpies of fusion or enthalpies of vaporization, and they made it slightly easier for you to understand on this sheet. So what is this number, and what does fusion mean? We think of like a nuclear reactor or something like that. Well, fusion and vaporization simply say when a substance is changing a phase. So let's pretend down here we have ice. Now when ice gets enough energy into it right here, it starts to go through a change. This change right here is called fusion. It's called the heat of fusion of ice, or it could be of any other substance. Or I could say the enthalpy of fusion. So the actual definition is the amount of energy it would take for 1 mole of, let's just say, ice to change from ice to a liquid, so to change phase. And the term is fusion. So right here it's changing from ice to water. Think about when you put ice in a cup, it doesn't just all change to water instantaneously. Suddenly it's water. It gets smaller and smaller. That's what it's doing here. And as it's changing, all of the ice is changing. It's not going up in temperature. It's just staying the same. Now when all of it becomes water, it's right here. This is all water. It's all changed. Now the water is going to start boiling on the oven, right? So we're putting a whole bunch of heat into this. The temperature is rising. And I get here, and what's going to happen? Well, my boiling water is going to turn into gas. Yet again, it's going to take a while for all of it to turn into steam or gas. That's going to happen right here. There's a term for this. It's called the heat of vaporization. So fusion is changing from a solid to a liquid. The actual enthalpy of fusion is how much energy it takes to change 1 mole of a substance from a solid to a liquid. The heat of vaporization is how much energy does it take to take 1 mole of a substance and change it from a liquid to a gas. Okay, there's actually reverse terms though. What if I want to go from a liquid to a solid? It's not fusion. In that, if I do that, it's called solidification. It's the opposite. It's the reverse. What if I want to go from a steam back down to a liquid? That's called condensation. So the heat of condensation. I'm not going to spell the whole thing out here. So we have opposite terms. There's actually a term if I go from ice straight to a gas. That's called sublimation. If I go from a gas straight down to a solid, that's called deposition. So there's different calculations for all this. It actually takes a different amount of energy to change something from a solid to a liquid than it does from a liquid to a gas. And there are tables that are provided on the test or in a textbook for you to understand all of this. So right here, it takes 6.01 kilojoules per mole to change 1 mole of ice into 1 mole of water. And notice how it takes a lot more energy to take that water and turn it into steam. Okay, so then we have other substances, and every substance has different heats of fusion or enthalpies of fusion and enthalpies of vaporization. Yet again, these are provided for you, but pay attention to the units. I've seen some questions where instead of kilojoules, they might have calories per mole. Sometimes they even put this in grams. So think about this. If they give you grams of benzene, you're going to need to change it into moles to figure out how much energy it takes. So be careful. Always pay attention to the units. When in doubt, look at the units, try to convert it. Okay, we've already kind of gone over this. This is called a phase diagram. They vary for different substances. This just happens to be water. And what it does is it shows you a substance going from one phase, a solid, to a liquid to a gas. Now, it could be reversed. It could start over here. Then it's going to go from a gas down to a liquid to a solid. And the temperatures could be different, the time could be different, or it could just show one phase. So you got to learn how to read these, which we will do later. And there are some of these in the textbook and probably on a test. Okay, let's look at some basic equations. Probably your most common equation you're going to use is this Q means heat. Yet again, when you first look at it, you're thinking, what is all of this? This is just confusing. And when you see stuff like this, it's unnerving because you don't know it and you get worried. You think, man, this could be hard. And I think this is where people sometimes get scared of chemistry. Trust me, I'm exactly like you. And then that is the point in time when you have to sit down and buckle down and just sort of understand what this is saying to get more comfortable with it. So this says heat equals mass, so this is the mass of a substance, times the specific heat, and there's this weird little pyramid in T, so this is a change in temperature. So delta normally means a change. What that means is they'll give me a starting temperature, initial temperature, or they'll give me a final temperature, or they'll just tell me, and I need to put that number in here. This is normally in Celsius, so mass in grams, and then they'll give me a specific heat. This is going to be a common sort of equation we use quite a bit. Down here, these will be heat equals the enthalpy of fusion or solidification or vaporization, and these are the numbers they give us. And so these are other common sort of equations that we can use. Okay, let's look at a couple of basic problems because that's the best way to understand it. How much heat must be absorbed by 375 grams of water to raise its temperature by 25 degrees Celsius? So our most common equation is heat equals mass times specific heat times a change in temperature. Let's see if we can use this equation to answer this question. Well, it's asking me heat, so I need Q. I have mass, which is 375 grams of water. Okay, specific heat of water. Well, this is where they have to give you a chart. If I go up here, and remember it said water, so I need liquid. The specific heat of water is 4.18 joules per gram Celsius on this chart. 4.18 joules per gram Celsius. So let's put that down, 4.18 joules. And this is what I do to sort of help me understand these units. It's joules per gram Celsius. Why do I do that? Because then I can see if these units are going to cancel and I can make sure I have the proper units. Sometimes people write this, and you can do it however you want. Sometimes people write it like joules per gram Celsius. And that doesn't really help us a lot, I don't think. Especially if you're not comfortable with these sorts of calculations. And I've also noticed a lot of kids don't put the units. They just put the numbers. It's really important to put these units. They're there for a reason. And I am just like you. I get lazy. I just say, oh, I know it. I already know the units, and then I don't put the units. And then as soon as you do that, you get messed up. Okay, it says raise its temperature by 25 degrees. Well, here's the thing. They didn't give us a starting temperature, an initial temperature, or an ending. They didn't say we started it at 50 degrees and we entered it at 75. But they already gave us the difference, which is 25 degrees Celsius. So I can put this right here. And then, to find Q, I just do this math. 375 times 4.18 times 25, and I get the answer. And I notice my units cancel. Grams cancel. Celsius cancels. And so my answer is going to be in joules, which is energy or heat. All right, let's move down here. What mass of water can be heated from 25 degrees Celsius to 50 degrees Celsius by the addition of 2,825 joules? Okay, this is one of those things where we have to be able to rearrange these equations. They could give us the mass, the specific heat, the energy, and then ask us what the difference in temperature is. So there's a lot of things they can do here, and we have to be comfortable with rearranging equations in chemistry. And I've noticed that sometimes that sort of scares students too, but don't be scared about it. So we need mass. This is the number we need. So how do I get this on one side? I need this on one side of this equation. Well, if I divide, well, let's just say it this way. If I multiply both sides by 1 over the specific heat and the temperature change. Whatever I multiply this side by, I have to multiply this side by. So I would do it there also. Okay, this is all going to cancel. So really on this side, I'm going to get M. And on this side, I will get Q over, I'll just say cat, because I like to say cat, because they're cool animals. Now, and then if it makes you feel better, you can rearrange it and write it like this. M equals Q divided by cat. Because I always kind of like it on the left, but it means the same. So now let's do this. What mass can be heated from 25 to 50 degrees. So basically, actually, I'm sorry, I said T initial. It's actually T final minus T initial. So my final is 50. My initial, so it's 50 minus 25. So down here, it's going to be 25 degrees Celsius. And then I need the specific heat, but yet again, it's the specific heat of water, which I already know is 4.18 joules. 18. And let me get some space here. 4.18 joules, right, per gram Celsius times 25 degrees Celsius. And then up here we have 2,825 joules. So it's a big old huge mess here, basically, if we write all this out. Let me get rid of all. So I did this just to say, well, these Celsius is going to actually cancel. So if I do this math, 2,825 divided by 4.18 times 25, I'm actually going to get my answer. I will get my answer, and by the way, these joules were canceled too, so my answer is going to be grams. And if I did all this math, I'm going to get 27 grams, and that will give me the answer. Okay. I hope this isn't confusing anyone. I just like to show a lot of examples because then the more examples we have, the better off we are. What is the final temperature when 625 grams of water at 75 degrees Celsius loses? And whenever people see this, they're like, OMG, look at what is this? Well, it's just scientific notation. It's a big number, but it's nothing to be scared of. And we just use it like we use all the other numbers. So we have Q equals MCAT. Okay. Well, this is weird. They want the final temperature. Okay, well, so we're going to need, this doesn't give us the final temperature. I need to find this number here, though. And then we'll see what we can do. So we have 625 grams right here. So we have 7.96 times 10 to the fourth joules equals 625 grams, yet against water, times 4.18 joules per gram Celsius, right? But I have this right here. Okay, well, how do I get this on one side? I need the t, the delta t on one side of this equation. So yet again, I'm going to have to take all of this and put it over here. So 7.96 times 10 to the fourth divided by 625 times 4.18 joules. Okay? I hope that wasn't confusing. Okay, when I get this answer, I'm actually going to get 30.23. Here's the weird thing. This is why I wanted to show you this question. That's not the answer. This answer is delta T. So what this is telling me is that this is the change. This is the amount the temperature changed. It changed 30.23 degrees. Now I have to take this number and I have to ask myself a question. Okay, well, I was at 75 degrees, right? Because if I read this, what is the final temperature when 625 grams of water at 75 degrees loses? So what is the final temperature? Okay, so it started at 75 degrees. It lost minus 30.23 degrees. And then that will equal about, 44 degrees. I'm rounding off. So the answer asks the final temperature. The final temperature is 44 degrees. So yet again, it's important to sort of pay attention on that one because you could easily get confused and miss that question, which is why we always do a bunch of examples, which Just makes you feel better inside, doesn't it? Just makes you feel happy and fluffy. Okay, just a couple more, then we'll be done. How much heat in kilojoules is absorbed when 24.8 grams of H2O liquid is converted to steam? Okay, I wanted to show you this because we cannot use this equation right here. This equation only works when something is changing temperature. Okay? So if I look at the phase diagram, this only works if I'm in here or here or here. It's changing temperature. It doesn't work when it's changing phase. If something is changing phase, I need to use a different equation. So if something is changing phase, I just use Q, the heat, equals the enthalpy of whatever I'm doing. Right here, I'm going from liquid to gas. You have to look at the terminology. Steam is gas. I'm going from liquid to gas. It's liquid. So that is called the enthalpy or molar heat of vaporization. Okay. So now I need to go back to my little chart. It was liquid. I go down here. The heat of vaporization is 40.7 kilojoules per mole. 40.7 kilojoules per, I'm going to write it over mole so it doesn't confuse us. Q equals. Now, why do they even give us the temperature? You're thinking, why is this even here? Because at 100 degrees Celsius, water boils, and that's the boiling point of water, which is given to us on this table, but in Kelvin. Here we have the boiling point, 373.2 Kelvin. So it's basically 100 plus 273. So we need heat. We have 24.8 grams. Sorry, I should have put mass in here. Q equals mass times the molar heat of vaporization. See here it's mass times the specific heat and then the change in temperature. So the equation is different. We just put 24.8 right here. So we have heat equals mass times the molar heat of vaporization or the enthalpy of vaporization. And these numbers will be provided for you on the test. So if I do this, and by the way, this is in grams. But if I'm looking at this, I got a problem right away. And I almost did the exact same thing I told you not to do. See how easy that is? My problem is I have grams, but I need moles. So I'm going to have to convert 24.8 to moles. If I have 24.8 grams, of water, I will do a little easy conversion. 1 mole of water is, then I got to find the molar mass of water. So oxygen's like 16 grams and hydrogen's about 1, so it's like 18 grams. Now if I don't know that, they actually gave us the molar mass of water right here, 18.02 grams per mole. So thank you. 18 grams per mole. So what I would do is, the grams would cancel, right? And 24.8 divided by 18 will give me a number. So in the end, Q is going to equal 24.8 grams of water times 1 mole of water divided by 18 grams. Now I will use my heat of vaporization, which is going to be 40.7 kilojoules per mole. So I will take the grams, the mass, convert it to moles, convert it to energy. My moles will cancel, my grams will cancel, I will get kilojoules. And in the end, I'm going to get around 56.07 kilojoules. Do the happy dance. You got an answer. Okay, how many grams of ice will melt if 2.25 kilojoules of heat are added? Okay, this is weird because it actually gave us the heat. So instead of using Q equals mass times the, and this is solid, a solid going to a liquid, so it's actually the enthalpy or molar heat of vaporization. So I have 2.25 kilojoules equals M times, I have to look up here, my heat of fusion. My heat of fusion, sorry, I said vaporization. Should be fusion. See, I make mistakes. My heat of fusion is 6.01 kilojoules per mole. 6.01 kilojoules per mole. And then, yet again, I got to get this M on one side. So actually, it's going to be M equals 2.25 kilojoules divided by, I'll just take this and divide it, 6.01 kilojoules per mole. Okay? And here's the weird thing about this. This is kilojoules per mole. So in the end, once I do this, say I take 2.25 divided by 6.01, I'm going to get 0.37 moles. My answer is in moles, but I need grams. So what do I do now? Well, now I just convert moles to grams. So 0.37 moles equals, I did my conversion factor, 1 mole equals 18 grams. So I take 0.37 times 18 and I will get an answer. Now my answer will be in grams of water. So yet again, these equations are easy to understand, but we have to understand how to rearrange them and how to change them into the units we need to do. We need to get the answer. That's the tricky thing. Okay, last one. Calculate the amount of heat in kilojoules required to decompose. Now, I wanted to show you this because this is completely different. This is an equation. This is a thermochemical equation. It's thermochemical simply because it tells us how much energy we need for this equation to happen. Notice how it's on this side. It says plus 85. If you have energy on the left-hand side of an equation, the equation is actually endothermic. Endothermic. So this needs energy for this equation to happen. Now, if I move this over here, let's just say it's on this side, it's like minus 85 or some number over here, then it's exothermic. Heat is being produced. So exothermic means heat's being produced. Endothermic means it needs heat for this equation to happen. And this is actually very simple. We just use conversion factors when we see these types of equations. So it says to decompose 2.24 moles of, what is this, sodium bicarbonate. So I look over here and you're thinking, how do I do that? Well, let's just use our conversion factors. I have 2 moles of this stuff right here. 2 moles of sodium bicarbonate. How much energy does it take for 2 moles? How much does 2 moles need to convert, to decompose? It needs 85 kilojoules. So that's a conversion factor. 2 moles needs 85 kilojoules, but I have 2.24 moles. So now I can easily say, well, I have 2.24 moles of this stuff. It'll all cancel. So really, in the end, I'm just going to take 2.24 times 85, divide it by 2, and I'll get 95.2 kilojoules. So that's how you answer those sorts of questions. I just wanted to show you that because I want you to know endothermic, exothermic, and how to read a thermochemical equation. We're going to have more of those. Okay, well, that's enough for now. I hope that helped you out. Like usual, if you have any questions, let me know, and I will try to help.